Our universe, a vast and endless expanse of galaxies, stars, and planets, is a treasure trove of mysteries waiting to be unraveled. As we journey through the cosmos, we encounter myriad of intriguing possibilities that challenge our existing knowledge and understanding. One such possibility that we shall explore today is a concept that emerges from the realm of quantum physics: the concept of vacuum decay. This brings us to an interesting question. What if our universe exists in a state that merely appears stable? A state known as a false vacuum. This curious state is a product of quantum field theory, a fundamental theory in quantum mechanics that explains how particles interact with each other. However, this false vacuum, despite its seemingly stable nature, might not be the most stable state our universe could be in. But what does it mean for this false vacuum to decay? And what would the implications be for our universe? As we delve deeper into this fascinating concept, let's explore its implications for our broader understanding of the universe. Remember, the universe often hides its most profound secrets within its most complex phenomena. A false vacuum is a state of matter that appears to be stable and at rest, but is in fact in an excited state. If this sounds complicated, let's make it easier with an analogy. Visualize yourself sitting on a hillside. You seem at peace, yet any moment could start rolling down. This is similar to the false vacuum decay, the transition from this seemingly stable state to a more stable one. In the fascinating world of quantum field theory, a false vacuum is akin to sitting on that hillside. It appears stable, it feels comfortable, but it's not the most secure state. The Higgs boson, a particle that exists level, plays a crucial role in this theory. The false vacuum isn't just a theoretical state, it has real-world implications. It is hypothesized that a false vacuum could exist at a higher energy level than the true vacuum, meaning that a transition from A to vacuum would release energy. This transition, called false vacuum decay, is a quantum tunneling event where the universe's state changes from the false vacuum to a lower energy true vacuum. This process would be highly energetic and could to catastrophic outcomes, obliterating everything it comes into contact with. But fear not, the likelihood of this occurring is incredibly low. Even if it did happen, it would probably take trillions of years and coincide with the natural end of the universe. Now that we have a basic understanding of a false vacuum and the intriguing concept of false vacuum decay, let's delve into the Higgs field and Higgs boson, which are intricately linked to this concept. The Higgs field is an energy field that exists throughout the universe, and the Higgs boson is a particle that accompanies this field. The Higgs field, in essence, is like an omnipresent cosmic molasses. It permeates every nook and cranny of the universe. As particles move through this field, they interact with it, and it's this interaction that endows them with their mass. Imagine particles as swimmers, and the Higgs field as the water in the pool. The more a particle interacts with the field, the heavier it becomes and the slower it moves, just like a swimmer trudging through water. Now let's talk about the Higgs boson. This elusive particle is the physical manifestation of the Higgs field. It's like the ripples created when you throw a pebble into a pond. In the 1960s, physicist Peter Higgs proposed its existence, but it wasn't until half a century later in 2012 that scientists at CERN were able to confirm it. The discovery of the Higgs boson was a monumental achievement, as it was the last unverified part of the standard model of physics. The Higgs boson plays a crucial role in all physical forces. Along with other known bosons such as the photon W and Z bosons and gluon, it's responsible for mediating the fundamental forces in our universe. However, detecting the Higgs boson is a challenge due to its substantial mass and fleeting existence. That's why scientists had to build the Large Hadron Collider at CERN, a gigantic machine designed to collide particles at high speeds and create conditions where the Higgs boson could be observed. So, in summary, the Higgs field is like the stage on which particles perform, and the Higgs boson is the lead actor, playing a critical role in the universe's grand performance. With our grasp on the Higgs field and Higgs boson, we can now better understand the concept of vacuum decay. Vacuum decay is a theory suggesting that if the Higgs field releases its potential energy, it could create a cascade effect, leading to the destruction of everything it interacts with. Let's delve deeper into this intriguing notion. Vacuum decay is a hypothetical event rooted in quantum field theory. This theory proposes that our universe as we know it might be in a state of false vacuum. In simple terms, we're in a stable state, but not the most stable one possible. The transition from this false vacuum to a true vacuum is what we refer to as vacuum decay. Now imagine the universe as a landscape of hills and valleys, with each valley representing a different vacuum state. We're currently in a valley, but not the lowest one. If we were to somehow roll down to a lower valley, that is, if the universe were to transition to a more stable state, the effects would be catastrophic. This transition would occur in the form of a bubble, originating at a single point and expanding at the speed of light. Within this bubble, the laws of physics would change dramatically. All structures, galaxies, stars, planets, and even atoms would be torn apart, and the universe as we know it would cease to exist. However, before you start panicking, let's put things into perspective. The chances of such an event occurring are infinitesimally small. In fact, estimates suggest that the natural risks of vacuum decay destroying the Earth are less than 1 in 10 billion per year. Furthermore, even if such a transition were to occur, it would likely take trillions of years, probably coinciding with the heat death of the universe. In essence, vacuum decay is more of a fascinating thought experiment than an immediate concern. It allows us to explore the boundaries of our understanding of the universe and the laws that govern it. It's a testament to the rich and complex tapestry of theoretical physics, where even the most stable elements of our reality can be questioned and explored. As we can see, vacuum decay is a fascinating concept that pushes the boundaries of our understanding of the universe and its stability.